we've looked at linear functions and quadratic functions, constants, all that kind of stuff. But let's talk about polynomials of a higher degree. So polynomials in a higher degree are in the form of y equals ax to the power of n plus a n minus 1, aka previous, x to the power of n minus 1, dot, 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 dot. Okay, so kind of confusing, but realistically, this is in the form of some number x to the third plus some number bx to the second. So the coefficients doesn't really matter, but the exponents, they have to go down in descending order, in numerical order. If you don't have something, you can skip terms, and that's fine. Whatever has the highest degree, so the highest exponent, remember, is the leading coefficient or leading term. Okay? So when we're looking at polynomials of higher degree, we're going to be looking at specifically what happens with, you know, the local extrema and that kind of stuff. What happens if you move it? So for instance, if I were to have y equals 3/4 x minus 1 to the power of 3 plus 6. Okay, so how does this compare to the parent function of y equals x cubed? Okay, so looking at this, we should kind of already have an idea that the vertex, or what we consider based off of that x cubed, is already going to be shifted to the left, sorry, to the right 1 and up 6. But let's go ahead and check this out based on Desmos, just as a matter of fact, to double check, you know, what's actually going on. So for instance, y equals x cubed is my parent, and then I have y equals 3/4. We'll close that parenthesis there, and then I've got x minus 1 to the power of 3 plus 6. Okay, so looking at this, I can see here that this is kind of my vertex in terms of, okay, we went through the origin. This is where we're kind of having a change in our concavity. So that change got shifted to the right 1 and up 6. And that was based off of our transformations, which we've talked about before, just what happened. So if I were to take those away, what happens with just the 3/4 there? If you notice with the 3/4, it really didn't change a whole lot, but the branches did stretch away, like we've talked about. Now, because that's a fraction out in front, if that were a number, say like just a 3, those branches would get closer to that y-axis. With that, you're then going to be asked to find, you know, extrema values. So for instance, you know, your local mins and maxes, anything of interest. With that being said, there is one other thing that is very important to note, and this is what we call the end behavior model, or the end behavior. So the end behavior is similar to what we were doing with horizontal asymptotes. We were looking, as we're going to the left, what is happening to the graph. As we're going to the right, what is happening with the graph. Okay, so with that being said, let's look at a function of the form Sorry, I needed a definition for end behavior. Let's look at the function in the form of f of x equals x plus 3, x minus 2, and let's go with, 2x plus 3. Okay, so if I were to look at this, I'm supposed to, look for my local extrema. I'm supposed to figure out the x-intercepts and also the end behavior, what's happening to the left end, what's happening to the right end. Okay, so with all of this information, you could technically find your x-intercepts by hand in this setup because it's already in factored form. So the x-intercepts, you could set each parenthesis equal to 0 to find those x-intercepts. If it's not in factored form, you could still use Desmos, and that would get you the same results. So looking at this, the x-intercepts, I'm going to make that parenthesis equal to 0, and I'm just going to solve for x. So x is going to be -3 here. The next one is going to be at +2. And then this one is going to be at -3/2. So those are my x-intercepts. Now, based off of that factored form, you aren't probably going to know, okay, what are the local mins and maxes based off of that? And that's totally fine. You're going to go to Desmos and look at your graph of that. Let's see here. Sorry, just trying to move things around here. Oops. And then I have, what was it, 2x plus 3? Double check, make sure I have this correct. Whew, you never know. All right, so looking at this here, I can find my x-intercepts based on my graph. It tells me where they're located. We did all right with that, so no problem. I'm going to zoom out a little bit just so I can see all of my points. So this we already know is going to be my local max. You would just need to write down your coordinates there. And this is going to give me my local min. So the end behavior, looking at this, what this represents is as we're approaching, as x is approaching -infinity, ooh, sorry, starting to write an 8. So this is just, remember, this is just the fancy notation. As the limit is approaching -infinity, aka the left, what height is that graph going towards? So as I'm going towards the left, where's the graph going towards in terms of height? Okay, so in terms of height, it's going to keep going down forever, so it's going towards -infinity. So now we're going to do the same thing for the right-hand side. This time we're approaching +infinity. Where's it going? So as I'm going this direction towards the right, where's that height going towards? That height, if we can look at that, is going towards +infinity. Now, it won't always end up this way, that it's +infinity or -infinity. It could be actually going towards a value, or they could both be going towards, both be +infinity or both be -infinity. It doesn't always have like a set rule of paths. So you're just going to have to look at that and see, where is this going? Okay. So this is just limit notation. Again, -infinity is going towards the left. This +infinity is going towards the right. So if I were you, I would make sure that you have those limit notations written down, because you will want that for future reference.